how are we going to do on sound here? Do you think my voice is going to carry here, or is that going to be good?
Yeah.
All right, I think we have a microphone just in backup, so if my voice drops during the talk, just give me a hands up or something, and I'll grab the microphone. So yeah, thanks for inviting me out to come here. It's nice to be in front of you to give this talk. I am Robert Quimby. I am from San Diego State University. I've actually been there a bit longer than the introduction says. I got there in 2014, same time as I took over as director of the Observatory. So what I'm going to do today is I'm going to tell you a little bit about the research that we do at our observatory. But along the way, I want to just more generally, give you an idea of what do astronomers do? What is research? How do we actually study the universe? It might be a little bit different. What I actually do is probably a little bit different than the picture at least some of you may have in your heads right now. So let's talk about that. Let's actually start with this picture in the background here. I didn't take this picture. This is not mine. I just did a Google search and found a nice pretty picture. But it's a real picture of the sky here. And if you look at it, it's beautiful, first of all. Have you guys ever gone out and seen the sky like this? Maybe not quite like this. This is the magic of photography. You can do a little bit better than your eye. But I used to go out. I was an amateur astronomer when I grew up, and I used to go out with my family, out in Ansburigo even, and we'd look up at the stars. And so I know some little stories about the sky. I know that this is the constellation Scorpio. Thank you for Scorpio here. And let me just grab the mouse. Maybe you can see the mouse to it. So Scorpio is kind of bigger than this. This is kind of the head of the scorpion here. And this is its body, and it goes down here. There's this tail that kind of loops around.
Yeah.
You see it? It's one of the few constellations that really looks like what it's supposed to be.
Yeah.
It's got that tail there. And then there's actually two pincers as well that go around. They go off the screen here, but you can see that. So it really looks like a scorpion. It's kind of amazing. And right in the heart here, we've got a star there, a red star, right where the heart should be. And that star has a name, and it's Antares, or Antares. I don't know how to pronounce things, but I know it's two parts. One part is anti, which means opposes, and the other part is Aries, which is another word for Mars. Right? It's kind of the same color as Mars. So this is Mars' rival, that star. So that's where it got its name from. You see that bright blue star right there? Do you guys know the name of that one? Anybody? I don't know it either. The only star that I know in this entire field is Antares, right there. That's the only story I can give you about this. I can't tell you any other stories about the constellations. I can point out the teapot here. It's not a real constellation. But if you're an amateur astronomer, you know there's a handle here, there's a spout right here. It kind of looks like a teapot. It's got the steam cloud coming out of it. So I know these little things, but that's all amateur astronomy. So if you want to know the name of that blue star there and some of the other constellations in this field, I heard about that event coming up. Is it next week or?
31st.
Coming up soon? 21st. There you go. That's probably a great time to ask those questions. Those amateur astronomers, they're fantastic. They know a lot of the stories, a lot of the names. But that's not what we do as professional astronomers. I never took a class that told me to memorize the names of constellations. I don't know them all. I know a handful of star names, but I really don't know that many. We don't do kind of the historical side of astronomy as a researcher. What we do is we ask questions and try and figure out how our universe works. So we look at a picture like this and we say, that star's red, but that one's blue, that one's white. Why are they different colors? Good answer. We try and figure that out. How do I figure this out? I can read a book and it'll tell me, well, it's because of the temperature. But someone had to figure that out. Someone had to go and say, how do we know what the temperature of that star is? I can ask how far away are these stars? Again, there might be a book in here that tells you how far away maybe Antares is, but I bet it doesn't say how far away that star right there is. So if I want to know how far away that star is, what do? How do I figure it out? What are the stars made of? What kind of gas? It's definitely made of gas. How do we figure these things out? That's what I'm going to do as a professional astronomer. Is I'm going to try and answer these questions, not by doing research in a library, but actually by getting a telescope and going out and studying the sky. Now the key thing is, to answer one of my questions, or to give a hint at least, these stars are really, really far away, like really far away. So we can't go there to study them. I can't get in a spaceship. Even if one existed that could take me out there, it would take more than my lifetime to get to any of these stars. So, I'm in a hurry. I want to know today. Like, how can I figure this out today? So that's what we do as astronomers, is we try and study objects that are so far away we can't interact with them. I can't touch it. I can't stick a thermometer in it to measure its temperature. I can't taste it to see what it tastes like, what it's made of, or take some gas and put it into a laboratory and study it. All I can do is just look at it. And just by looking at it, I need to figure out how this universe works.
Is it possible that you see a star on Earth that is no longer there?
This is true, yeah. So another fun thing is that it does take light time to go a certain distance. So right now you guys are, well, let's say 15 to 30 feet away from me. So you're actually seeing me in the past, right? So light moves about a foot in a nanosecond. So you're seeing what I look like 15 nanoseconds ago, 30 nanoseconds ago, which is much faster than your brain can process. So it feels like it's instantaneous. When you're looking at stars, okay, this star here, maybe that is, the light hasn't been traveling maybe 1,000 years. So if I could instantaneously go there, it might look different right now than it did 1,000 years ago. Have you guys been to the Mount Laguna Observatory? Some of you have. I want to make sure you know this. There actually are astronomers in San Diego. We actually have a reason that we're here. It's because there's some famous observatories here. You guys probably know Palomar, right? That's more famous. That's off the map up on the top. We're right here. We're also in the Cleveland National Forest. So there's some advantages and some disadvantages of that. But there's kind of two reasons why you put observatories out in the mountains. We could put an observatory here, but there's some problems with that. Obviously, light is one problem. So when you're in a city, there's lots of people, and we have lights at night, and we shine them up, and that produces a glow in the sky. And you guys know this. You go outside at night, and you can see some stars, but it didn't look like that picture I showed you a minute ago. You can't see all of them because of what we call light pollution as astronomers. That light that if you have these street lights here, I'm going to pick on that one right there, that pole light there. The light goes out, and it goes out too, and it bounces off a cloud and then comes back to your eyes. So you're illuminating the sky, the clouds, whatever's up over your head, and that's blocking, it's confusing, I should say, the starlight. Stars are still there, it's just harder to see. So you go out into the wilderness where less people live, and it's darker. The other reason why you go to the mountains is we kind of joke that we're closer to the stars when you're on the top of a mountain, but there is some truth to this in that we are above a lot of the Earth's atmosphere. You guys notice when you go up to the higher elevations, your ears pop, right? There's less atmosphere up there. So if you have a telescope, you got to look through the Earth's atmosphere, and then you can see the starlight coming through. And we don't want to look at the Earth's atmosphere, right? We're astronomers, we don't want to look at the starlight, so we want to be above as much of the atmosphere as possible. So that's why observatories are always out in remote locations. This is a picture that one of the cameras, we have this little camera at our observatory that just looks straight up, and it's kind of a fisheye lens, so you can see the entire sky. So this is a real picture of what it looks like at Mount Laguna Observatory on a dark night, the night when there's no moonlight. If you haven't been there before, you haven't been in a while, the Milky Way, you can see going across here, is bright and obvious. You go out there on a dark, moonless night, you can look up and there's the Milky Way. Not going to see the Milky Way too much from Coronado. Probably not. This is where we were just looking, by the way, this little patch right here itself. And you can see we were talking about the light pollution. Well, there's the direction of San Diego. We're about 44 miles away from San Diego, but in that direction, you see all this light here? That's the light from the city. bouncing off the atmosphere and coming back to us. So there are stars here, right? It's no different than over here. See all these little stars down to the horizon? You should be able to see stars down to the horizon, but you can't because of all this light pollution here. Right, so again, that's why we go out into the wilderness, out away from all the other people, so it's nice and dark there. We have several telescopes at our observatory. It's not just one, we've got quite a few.
Wow.
If you ever go up, I wish I could open to the public all the time, but we don't have the staff, so we can't do that. But we do make an effort over the summers. We have a limited number of programs, so maybe once a month or so. It's not much, but over the summer, a couple times at least, we'll open the observatory to the public, and you can come and look through the Polar Telescope. It's a beautiful little telescope, and you guys probably wouldn't say little. It's this big around and that long, so it's probably a big telescope. It's the smallest one we have at the observatory though. And we use that, it's dedicated for what we call eyepiece observing. You just look through with your eye and you can see the sky. And we invite people up sometimes for public viewing. And during the year, so when SDSU is in session, we have class trips that go up there, and our students get to look through as part of their lab classes. So in the summer, when there's no SDSU class, you guys can hopefully get a peek sometime. This is our biggest telescope right now. It's a little hard to get scale in this picture, but that's a roll of paper towels right there. Give you some idea. It's a pretty good sized telescope. It's a 1.3 meter mirror in there. So inside this box here, under these covers here, there's two petals that open up, and there's a mirror inside there. The diameter of that is 1.3 meters or 50 inches across. People often ask me, well, how powerful is this telescope? There's different ways I can quantify power, but the one that means the most to an astronomer is how much light can you collect with this? So that's what we're doing, right? We're trying to collect light from faraway places, and the more I can get, the fainter objects I can see, the farther away I can see. So I can compare it to the power of your eye. This telescope collects 21,000 times more photons per second than your eye does. Right? And when we take pictures, I'll talk about this in a little bit, we actually open up the shutter on our camera and we leave it open for a long time. So we collect lots of light for maybe 5 minutes, 10 minutes, 15 minutes. We'll just collect light, and then we'll have one image. So that each image, actually, you can go 1,000,000 times fainter than you can see with your eye. This is the telescope that's been there longer. That telescope I just showed you, the Phillips Claud telescope, is brand new. This is our older telescope. It's been there since the early 80s. And there's a couple of my students to give you some scale for here. So this is it's a little bit smaller telescope. It's a 1 meter diameter. So at the base here, there's a mirror that's 1 meter in diameter. And the way the telescope works is that you point where you want the light from, and it comes in through the top of the telescope, and it bounces off the mirror here. And then there's a second mirror near the top of the telescope. I'm going to show this better in this other image. I go back. So there's a mirror down here, and then you see up there, that little circle, that's the secondary mirror. So light bounces off here, goes up there, and then there's a hole through the primary mirror, the first mirror here, that goes down, and then you can just barely see it here, there's a camera on the bottom. So we have a digital camera, and we're taking pictures with that digital camera. So this telescope, this is a 1.3 meter, this is a 1 meter. You might think, well, 1 meter, 1.3 meter, about the same. But it's actually got close to half the light gathering power, because the amount of light you collect goes with the square of the radius. Remember that formula for the area of a circle, right? So if you make it a little bit bigger, you actually collect a lot more light. But this has been used for decades. Our students still use this. This is our main research telescope, especially for our master's program. Our master's students use this for the research. All right, so what we're doing, mostly with these telescopes, is we're taking pictures of the sky. So we need a good camera to do that. And we have this camera. This is the detector on our camera. Give you some idea of the scale of the hand there. So it's a little, everyone's got a camera now, right? We all carry around in the back pocket. It's a similar kind of technology as the camera you have in your phone, but a much bigger detector. But same idea, light comes in, you'll have a photon light that comes in, and there's individual pixels on this detector, and when a photon comes in, it knocks out an electron. This is photoelectric effect, and it makes a voltage on here. And then we can read what that voltage is and make a measurement of how much light do we get. So the more light that comes in, the bigger that voltage is going to be. So we're measuring how many photons we're getting just by looking at how much what the voltage is on this detector. Our camera is a little bit different than the one that you have on your phone. There's a little bit slightly different technology, but very similar in how it operates. One big difference is that we're trying to get pictures of things that are really faint, much fainter than you typically, when you're taking a picture of your cat, usually you get the lights on and it's nice and bright. When we're taking a picture of some distant galaxy, we want just the light from that one galaxy to, we just want to measure that, and we don't want to measure anything else. So we have to worry about something called thermal noise. We have a detector here, and we're trying to detect one photon that comes in and hits our detector and makes a voltage. Well, it turns out if you have many atoms and they're all together and they get a little bit warm, they start moving around and bumping into each other. And sometimes they can bump into each other and knock out an electron. So just the temperature of the sensor, just alone, can create a signal that we don't want to measure. So we keep our detector very cold so that basically the atoms don't move around as much, basically frozen in place. And so the only thing that matters is when a photon comes in, that gives us the signal. We keep it very cold. I say very cold, and you probably think freezing or a little below freezing. Our detector is about 200 degrees below zero. We keep it very cold because we're trying to get very accurate measurements. So while everyone has there's probably $15 worth of camera in here. Just this chip alone, when it was bought, it was probably $50,000 chip.
Wow.
Costs have come down. The scale is starting to, the economy of scale is starting to improve a little bit, so they don't cost quite that much anymore, but they're still pretty expensive cameras. All right. You guys want to see what we do. Here's a picture I took. Actually, I didn't take this. One of my students took this picture with our 1 meter telescope. Let me explain what you're looking at here. So first of all, I want to give you some sense of scale for what you're seeing here. So when you go out, next time you see the moon is pretty full right now, so you wait a little bit after sunset, you'll see the moon rising up in the east. All right, so what you do is to put your thumb out like that, and you can do this right now actually, just because it makes me feel good. Do this. Picture the moon rising on the horizon and look at your thumbnail. How is the size of the moon compared to the size of your thumbnail? What do you guys think? The moon would be like this big compared to your thumbnail?
Yeah.
Or your thumbnail, or it would be smaller than your thumbnail?
No.
So guess what? The moon is actually maybe 1/4 the size of your thumbnail. It's tiny. It's we say it's a big pizza pie, but it's actually a pretty small pizza pie. You should go down and take a look. So do this, because it amazes me too, because I have that picture in my head of the big moon rising on the horizon, but it's an illusion. Put your thumb out. You can completely, easily cover the whole moon with your thumb. Same thing with the sun. You can do that too. This field of view here is smaller than the moon. So that means you take your thumb, you kind of divide it into just a little fourth, your thumbnail. Take that and divide that into a fourth. And that little tiny piece is about how big this field of view is on the sky. Tiny little patch of sky that we're looking at here. And this is a long exposure, so we're looking at things that are actually very faint. Right here, there's a big bright star. You can't see the star with your eye. This is fainter than your eye can detect. The brightest thing in this field is way fainter than your eye can detect. There's another star up there. There's a star here, there's a star there, star. You see that right there? It's not a star.
Beautiful.
That's a galaxy. There's a galaxy here. There's a galaxy here. That's a little galaxy next to it there. That's probably a galaxy, 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 galaxy. All these little faint little smudges you see, those are all other galaxies. And they're all dancing in that tiny fraction of a thumbnail at arm's length.
And what's between the galaxies? Nothing?
There's more than nothing, but not much more than nothing. It's mostly empty space, but there is a little bit of gas that goes out between galaxies. Was there a question in the back?
Yeah, with the galaxies, can you see individual stars in those small galaxies or not?
Good question. So with this camera, I cannot see individual stars for this particular galaxy. This galaxy is too far away. There are 100 billion stars in this galaxy. And you can almost see, I can see individual pixels here. So there's maybe 50 pixels across, 50 up. So let's say we got a few thousand, several thousand pixels, but billions of stars. So they're all many stars in each pixel. If it's a near enough galaxy and I had a telescope in space where the resolution is better, like the Hubble Space Telescope, we can actually detect individual stars. But not for most galaxies, only the ones that are very close to us. Another question?
So you said you take long exposures. Do you have movement problems with the sky? Do you get like smudge?
Ah, that's a good question. So our telescopes move while they're taking pictures. You would never know if you went in and you looked at one of our telescopes while it was taking an image, it would look like this. But if you went in an hour later, it would be over here. An hour later, it would be over there. Our telescopes spin around once every 24 hours. We don't let them do that, but if I let it go, it would just, once every 24 hours, it would go around like this. So it always keeps that star in that field of view.
But the camera itself, then, do you have to use like some sort of software to, because then the camera keeps changing, right, the picture itself?
That's another good question. So if the way we have our telescope mounted, you see this is the mount right here, the blue part. You'll notice that it's at an angle. So this plane right here, this round disc here, it's moving like that. This plane is actually parallel to the Earth's equator. So what happens is as the Earth spins around, our telescope spins, well, it technically goes this way. It moves the opposite way to keep the star in the same spot. So we have to move the telescope, but only in one axis. And then our camera, we don't have to move at all. There are other types of telescopes where this is a big problem, where you have a telescope that moves like this and like this. If you do that, then as you move across the sky like this, you have to rotate your camera. And that's how big telescopes work. Like Keck works like that. There's a big, huge instrument rotator. You have these like instruments that weigh a ton, and it just takes it and spins it around as it moves. The question in the back actually is kind of on the long lines of what I wanted to go with this. So you see the star here, and this looks like it's the big star in this field, right? It feels like this is the big one and this is a smaller star. Actually, this image contains no information about the size of these stars. I don't know which one is actually bigger. What's going on here, the truth is, I'll just tell you the truth. This star, that star, every other star in this image is smaller than 1 pixel on my detector. Much smaller. Way, way, way smaller than 1 pixel. Now, the puzzle, you see all this light coming out here. How can that light? This is glare from the star. So what happens is that light from that pinpoint star, very far away, comes through the Earth's atmosphere, and it gets blurred out. Just like if you look along asphalt on a hot day and you see those wavy lines, atmosphere does the same thing. So when light's coming down, it gets smeared out and it gets distributed across many pixels on my detector. But the actual star is just one little tiny pinprick, tiny fraction of a pixel in the middle of it. So I don't have any I'm not looking at the size of the star. I'm not looking at its shape. I don't know anything about its size or shape from this image. This picture was a special, I like to show this one. This is a special picture because it was taken during an earthquake. So you're asking me about does the telescope move a little bit? This telescope was moving during this exposure, but the earthquake was short. It was about 20 seconds. And this is a 10-minute exposure. So most of the time, the telescope's sitting there and it's moving, like I said, it's tracking, it's following the stars. And then for 20 seconds, it did this. And then it finished the exposure like that. That's not obvious at first glance, but we got this nice bright star here. So if I change the contrast, that's all I did. This is the same exposure. I just changed the contrast. If you'll notice, there's some little squiggly lines there. I can take the next exposure, this is the next one, and if I subtract off this light from the first one, this is what you get, the difference. And I can zoom in here, and I can see what's happening. The star was sitting right here in the middle. This is saturated, so it's black there, but sitting there, and then the earthquake happened, and it just jiggled all around. All right, so this is my 2D seismograph of the earthquake there. All right, so you might be wondering at this point, like I'm an astronomer, I want to study stars, but I can't even see how big a star is with my telescope. They're all too small. So how do I know anything about its size or, if there's a planet going around it, how do I do that? Here's one way we can do that. Let's stop. There's a little video here. There it is. Because it's only going to go around one time, so we have to keep doing this here. Normally, if you're looking at a star, you're getting light from that star, and that's it. But let's say it has a companion. If you are lucky enough that orbit is in the same plane as you, so you're in the same plane as the orbit. If it's going like this isn't going to work. But if that star happens to pass in front of that, let's call this a planet. If this planet passes in front of that star, oops. Then what happens, come on, there we go. Right there, when the planet passes in front, it's going to block some of the light from the star. Just a little bit, but it's going to block some. And that means that star is going to get a little bit fainter. So what we can do is we can look at the star and see how bright it is over time. Just keep looking at it, look at it, look at it, look at it. And we can compare this to another star. So there's two stars. This is time here. Sorry to show you data, but that's what astronomers, what we do. This is time in hours, so over kind of 4 hours, somebody used our 1 meter telescope and looked at this star and another star and just saw how bright it is over time. And eventually it started setting. That's why the red curve kind of goes down, because it was high in the sky and then it got lower and lower and started looking through more of the Earth's atmosphere. More and more, and it gets more obscure and harder to see and less light comes from it. Same thing happens to both stars, but this one also had this little dip right there and up like that. This is the two stars divided by each other. So this star in black here is about 78% as bright as the one in red in the top there. And then it dropped down by about 3%. It got fainter for a little bit, and then it went back up again. And that is telling us that it's not just one star, that it's got a companion that went in front of it and blocked some light and went back. And this happens periodically, over and over and over. So, first of all, we can detect this and we can say that's not just one star, there's a companion that goes around it. And then we can look at this, and depending on how much light is blocked and how frequently it's blocked, we can figure out what the orbit of that star is, or that planet, what the orbit of the planet is, how big the planet is. We can figure out a lot about this just by studying this curve. And again, we can't see the planet. The star is way bigger than the planet, and we can't even see the star. It's just a point of light. Question?
In the military, I did a lot of celestial navigation.
Yep.
Where you're having to find a star and then you bring it on the horizon and figuring out where you're at on a lat long.
Yep.
And how does the people that develop those charts that you use to determine, I had Starfinder that said this is where I'm going to find on the horizon. A lot of it based on what they're doing there.
So if you're talking specifically about navigation, so what they're doing is they're recognizing that we're on a round planet that's spinning around, and it has some poles.
You have a celestial sphere that goes around.
Exactly. So what we can pretend is that all the stars are projected onto a celestial sphere, we call it, and they're just frozen there on that celestial sphere, and we're just on Earth spinning around. So all I have to do is first of all, is every time, let's just show you. I'll just keep this here. Every time the Earth spins around, one time, you go back and there's the same star should be in the same place.
Right.
So we're pretending that the celestial sphere is fixed and we're rotating around, and that's one time we rotate around and another time we rotate around, every time we do that. So what you can do is you can look at that star and say, oh, it's over there, so here's the time. Because I know in a few hours it's going to be up there.
And it's going to give you a good correlation with dates and where you can look in the night sky to find that particular star.
Yes, so the other complicated thing is we have the sun, right? So we're spinning around and we're also going around the sun.
Yeah.
So sometimes when we're looking in this direction, the sun is there. But other times when we look in that direction, we're looking away from the sun.
So I guess a lot of the tables that we use for that was stuff that astronomers do to find different stars.
Yeah.
And they just put it down, write it down this date. If you look in this sky at this, level, degrees, you're going to find what you're looking for.
Yep, that's right. There's a lot of that. That's kind of the classic astronomy research was just measuring positions of stars. Astronomy is measuring stars. Astrometry, measuring stars, and that's where it began. And the U.S. Naval Observatory still does a lot of this work, and still publishes. Here's the positions of these stars on these times, and you can use that to figure out where you are if you're a ship to sea. Yep.
So there was a movie a year or two ago that basically they were able to determine there was an exoplanet and a civilized exoplanet based on little squiggly lines in this kind of graph. Are you familiar with that? And is that
I haven't heard of a civilized exoplanet, like with people. I haven't heard about that.
it was fiction.
Oh, it's fiction. Okay.
But I'm just wondering if that level of precision is available in this sort of research.
So what I've shown you so far wouldn't be able to detect that. All you can say is there is a planet that's going around there. You can't see it even. So I can't say, well, they got tall buildings, or I can't say anything like that.
Right.
What I can show you in a minute is there is more information that we can get from that using what's called spectroscopy. So by looking at all the light, not just we're getting this much amount of light, but we're getting this amount of blue light, this amount of red light, this amount of green light, looking at all the colors and how much we're getting at each wavelength, we can learn a lot more about it. I'll show you that in just a second.
Okay.
All right. For now, I want to stick on just taking pictures. This is a picture I took. By the way, I study supernovae. That's my focus for my research. I study stars that are exploding. This is not that. I had a colleague who said, hey, there's this interesting comet. Can you take some pictures of it with your telescope? So I did. So this is the comet right here, a little fuzzy blob in the middle. And this is a movie here, so I can prove it's a comet. If you look sharp, you can see that it moves. Right? So all these other stars are fixed because they're on that celestial sphere we were talking about. They're really far away. The comet's much closer. So as it moves a little bit, we can actually see that motion. You see it move by us. If you look closely also, you can kind of see there's a tail coming by. It's a comet. Turns out this is a really interesting comet. The first thing you do when you get this kind of data is you try and figure out what's the orbit of the comet. So you take pictures over time, and you're mapping out where is the comet over time, and then you can kind of figure out, well, this is its orbit. It's going around like this and so on. Right? You guys ever see there's that Netflix movie, Don't Look Up? That kind of thing? Maybe? I got one in the back. But same kind of thing. So you see something, and no one had ever seen this before, a couple of years ago. So where did it come from? What's its orbit like? You start figuring it out. And this one's not coming right for us, so it's not like the movie. But there is an interesting story behind this, which is when they figured out what the orbit is, just by looking at these pictures over time, they found that it is not gravitationally bound to our sun, which means it's actually not going around our sun. It came from somewhere else. Right? So this comet has this name, Comet 2I Borisov. Borisov is the name of the person who first discovered it and said this is a comet. The 2 means this is the second object that was found in this category I, which is interstellar. This is an interstellar comet. It's the second object ever found that came not from our solar system, but from somewhere else and just passed through our solar system and went off and left. Yep.
Now, I'm sorry, but anyway, we get a good sense of direction here, like where this is in the 2D celestial sphere thing. how do we know how far away it is? And I would imagine you would have to get that information to plot its orbit.
Yes, so you can't do it from one picture, you can't tell how far away it is. That's a good point. But if I take a picture of it when it's here, and then I get a picture of it when the Earth moves, and I take a picture over here, let's say it didn't move, let's say just the Earth is moving. If I take a picture here and I take a picture here, I can compare this angle that I measure. That's what I measure with the telescope. What's the angle? And I can look at those background stars in the celestial sphere, and then I can triangulate. So this is how we measure distances for objects in the solar system. You wait for the Earth to move around, you take pictures at different times, and that gives you that third dimension. So we can measure pretty accurately what the orbit is. It's more complicated, obviously, because the comet's moving too. Yeah. So you need more than just 2 observations. You need several observations in a clever way to do this. Okay, so this is pretty neat. We got a comet that came from somewhere else. But there's more you can do. And I learned this. I didn't know this before because I do supernova. I don't study comets. But by looking at these data, you can actually tell something about what that comet is made of. Right? This is another video, by the way, where I just focus on the same pictures. I just focused on the comet in the middle, so the stars look like they're moving. All right, this is a busy plot. Sorry, this is the most busy one I'm going to show you. But this is showing us how we can actually figure out what kind of ice the comet is made of. This is the question. You got a comet that's coming from another star. It's coming from somewhere else. Is it the same kind of comet we have in our solar system? Let's find out. How do we do that? First thing you need to know is that a comet is a small little bundle of mostly rock and some ice, right? And when that rock with ice gets closer to the sun, the ice starts to sublimate and makes a big gas cloud, right? And as the comet moves, you get that big tail of gas. So the actual nucleus of the comet is a tiny prick, but all of this cloud of gas around it is a big screen that reflects sunlight and makes it bright. So the more melting and sublimation you get, the bigger that cloud is, and the brighter it appears. Right? If it didn't melt, it would just be this little tiny, faint little object. The gas that's going out is what makes it bright. So, depending on how much melting you get a different brightness. Now, different ices melt at different temperatures. There's water ice that melts at 32 degrees Fahrenheit, right? But you guys also used dry ice, right? It melts at a different temperature. So what that means is, if you had a comet that's made just of dry ice, it's going to melt farther away from the sun and make that big plume farther away from the sun. If it's made of pure water, it would have to get closer to the sun to melt. So depending on what type of ice you have, it's going to melt at a different distance from the sun. So we can measure its orbit, and we know how far away it is from the sun, and we can measure how bright it appears, and how that changes over time. We can find when does that ice start melting. That tells us what it's made of.
You know, I understand latent heat transfer, and so when it gets farther away from the sun, it's going to start regenerating and become larger?
No, so the ball heats up when it gets close to the sun,
Right.
just by the sunlight. It's just like lying on the beach and going, that kind of same effect, warms you up. And when it warms up, that gas blows off the surface, and the nucleus flies off, and that cloud of gas is gone. It's never.
Does the nucleus regenerate itself?
It does not. So every time it comes near a star, it loses a little bit of its mass, and it's gone for good.
So, but it stays basically the same mass throughout the journey?
It drops a little bit because there is water vapor or.
What about this interstellar, like what you were talking about?
Same thing applies here. So it formed somewhere, and it came by the sun, and it lost a little bit of mass as it heated up, and then it went off.
So it doesn't regenerate itself?
It does not.
It basically is just, I guess, infinite, and how long before it burns out, I guess?
Finite. It has a finite duration. It's a very long duration, but eventually it'll run out of
Like
ice.
Halley's Comet, that thing's been coming around every, couple decades?
Yep.
And it's still going.
Still going. It'll go for millions of years.
So there's no regeneration, it's just, okay.
Okay, so this is kind of what I'm showing here. So this is the distance from the sun in terms of how far away the Earth is. So this 2 means twice as far away from the sun as the Earth. 5 times away, 5 times the distance of the Earth from the sun. And what we're plotting here on this axis also is brightness. So these little squares are the actual measurements we took. And that orange line is saying if it only had dry ice, that's how bright it would be as it got closer and closer to the sun. It melts, it starts melting out here, starts making that cloud. As it gets closer and closer to the sun, it gets bigger and puffier and brighter. The blue line is for water ice. If it was only water ice, then when it was farther away from the sun, it wouldn't be very big because it would still be frozen. But as it got closer to the sun, eventually it would melt, and then you'd get that cloud. So what we actually see from this is it does have some dry ice in it, but it also has water ice in it as well. It's got both of those. It's actually very similar to the comets that we have in our solar system. And I figured this out, I didn't figure it out. Bryce Bolin, who did this research, he's the lead author, he figured it out just using those pictures. All right, I told you a little bit about this. I want to touch on it a little bit more. We can take pictures, and that's great. That gives us a lot of information. I can figure out how far away something is. We talked about triangulation. We talked about looking for planets going around and detecting them. And we can learn a little bit about composition just by taking pictures, as you saw from that, from the comet. But if we get spectra, we get a whole lot more information. So remember what a spectrum is. You guys, hopefully you've done this. You've got sunlight coming in, you put a prism there, it makes a rainbow. What that's doing is it's taking just the light from the sun and it's dispersing the light so that blue light goes over here and red light goes over here, green, yellow in the middle. It disperses the light. It doesn't change the light in any way. If I took another prism and put it on the other side, I could put all that light back together and you get white light again. Right? So this is just the contents of sunlight. Now we can look at this and we can say, okay, we got this much, how much blue light do we have relative to how much red light? If you got more blue light than red light, you're gonna have a blue object. If you got more red light than blue light, you got a red object. Right? So you can kind of figure that out. But there's also one very key point that allows us to figure out what stars are made of. And what that is that different types of gas. So let's say we got sunlight that excites some cloud of gas. I'll tell you what that means in a second. We can take the light from that cloud of gas in space, put it through a prism, and we'll get a different spectrum. We'll get a spectrum that looks like this. We're not going to get this. This is called a continuum, because you got all the colors in the rainbow. Here we don't get all the colors in the rainbow. We just got a few colors. This is a key property. And this pattern here of which colors we get tells us what that cloud of gas is made of. I look at this and I say, well, that's hydrogen. That's the fingerprint for hydrogen. That's the signature for hydrogen. Now, why does it do this? It's a little tricky, but come with me. Let's take this journey together here. You guys remember atoms, right? Atoms have a nucleus, protons and neutrons. They've got electrons. And kind of the cartoon picture is electrons are going around. Okay, they don't really do that, but we'll just pretend they do. They go around, and they have different energy levels. Right? So an electron can have this energy, or can have a higher energy level, or can have a higher energy level, but it can't have an energy level in between. You can have this level, you can have this level, you can't be in between those two levels. This is the quantized nature of the universe. Sorry to give you a little quantum mechanics, but that's where we are right now. There are quantized energy levels, which means discrete energy levels. You can be here, you can have this energy, you can't have an energy in between. Fundamental property of how our universe works. And we're lucky that this happens as astronomers, because what that means is, if you have some cloud of, say, hydrogen, and you excite one atom, you take that electron in there and you excite it to a higher energy state, eventually, it's going to drop back down to its ground state. It's excited, okay, and then it'll drop back down. When it drops back down, that energy has to go somewhere. Energy is conserved. So you had a higher energy, now you got a lower energy. Where'd that energy go? It makes a photon. And that photon has this specific energy. So you get a photon with either this energy or this energy, but nothing else in between. You guys with me? This is the tough part. This is the climb. So if you have just these allowed energy states, and you got excited electrons in a high energy state and they drop to a lower state, you get a specific energy level which corresponds to one specific wavelength, one specific color. So that's why there's nothing here. There's an allowed transition going from a level, this is a transition from level 2 to level 3, excuse me, to level 2, and you get this particular photon here. This is a transition from a higher level, maybe level 4, yeah, this is level 4 to level 2. It's a little bit bigger energy, a little bit higher energy, a little greener, bluer photon. So, hydrogen has this pattern, helium has a different pattern, oxygen has a different pattern, neon has a different pattern. I can tell you what the gas is made of just by looking at its spectrum without ever having to go there. I don't touch it, I don't taste it, I don't smell it. Just look at this pattern, and I can tell you what stars are made of, what clouds of gas are made of, what other galaxies are made of. All right, let me give you a specific example. This was done at our Mount Laguna Observatory. There's a star, I heard it earlier, Betelgeuse, right? You guys remember a few years ago, Betelgeuse did something a little strange? It got faint. I don't know if you got to see it, but I went outside one day and I looked up and that's not right. Betelgeuse was much fainter than I'd ever seen it before. And so there was a question, why did that happen? Well, there's different reasons stars get brighter and fainter. One is that something inside the star changed. So if the source of energy inside that star dropped a little bit, the star might cool down a little bit, and the cooler stars produce less light. So that's the first question. First possibility, maybe the star internally did something that caused the star to cool down, and that's why it looks fainter. The second possibility is if you got something bright and then something comes in front of it, it's less bright. So maybe there was some dust. These big stars make lots of dust, so maybe it just made a lot of dust, and that dust obscured the star for a while. All right, so we had a graduate student who worked with one of our professors, Doug Leonard, and tried to figure out between these two models what's going on. And the way he did that is by getting spectra of Betelgeuse. So I'm applying this a little bit different than I showed before. This is wavelength here, and I put the different colors here. This is roughly true. Different colors in the rainbow here. Our cameras can see colors that your eyes can't, by the way. You can go into the infrared and a little bit into the UV. And this line here is telling you how much light did it get at each one of these wavelengths. Right? So we got a little bit of blue light, we got some more yellow, some more red, lots actually of far red here. So if you looked at this star, you ever look at Betelgeuse? It's a red star. Got more light in the red than in the blue. Right? This is just telling you how much at each frequency they got. Now the key thing is that there are all these little features. We were talking about hydrogen. There's this little dip right here, that little line right there. That's not noise, that's real. That's telling us it has hydrogen in it. And there's sodium, and what else we got? There's iron lines, there's magnesium. But the key thing is that there's also molecules. Titanium oxide. Not a household name, titanium oxide, but it's one oxygen atom and one titanium atom put together. Now, the thing about molecules is that if you give them a little bit of heat, they tend to break apart. So this is actually a very sensitive measure of the temperature of the star. Our sun doesn't have any titanium oxide, it's too hot. If you had titanium oxide formed, it would break apart, and so we don't see this whole band here, all this absorption here, this is all caused by absorption from titanium oxide in the atmosphere of the star. We don't get this in the sun. But in Betelgeuse, we do. So what you can do is look at how deep is this, and if the star cools down, you get more titanium oxide and you get a deeper absorption trough there. So how deep this is tells you something about the temperature of the star. How do you feel about that? You trust me? Yeah. Okay. So what they did is they measured this over many, many days, and many different nights they went out. And what they found is actually the temperature of Betelgeuse during that dimming period didn't change. It's the same temperature. So that's telling us probably what happened was there was some dust that got in the way and just blocks them away. That's why it was different. Again, no, we didn't hire the graduate student to go and stick a thermometer in it. He might have been up for it, but it was a master's thesis, so you only get 2 years to do that, and it's not enough time to get the Betelgeuse. So we got Spectra. All right, maybe one more thing I can tell you about Spectra. We get a lot of information from Spectra. One key thing is that light behaves like a wave. Just like sound waves are waves, light sometimes behaves like a wave as well. And that means it has this effect called the Doppler shift. You guys know the Doppler shift, you've heard it. When an ambulance goes by, and it goes, wee, 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 whoa, whoa, whoa. Right? It starts at a high frequency when it's coming towards you, right? Wee, 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 and then it passes you and it drops. Right? That's the Doppler shift. Light does the same thing. I'm shining a light at you, and I come at you. I gotta come at you really fast, but if I come in your direction, the wavelength of light shifts to higher frequencies. If I go away from you, the wavelength of light shifts to longer frequencies. Longer frequencies are redder light, shorter frequencies are bluer light, so we call this red shift or blue shift. So what we do is we look at those individual lines, all those little absorption lines from the spectra, and we say, okay, compared to this maybe is a measurement done in a laboratory where we know nothing's moving, and we measure the star, and we see those same lines, but they're all shifted. That's telling us how fast that object is moving towards or away from us. This is our radar gun. We can actually measure the speed of a star along the line of sight moving towards or away from us just by looking at these lines. So we can do this again without actually resolving it or seeing it, just from the light. So another one of the professors at San Diego State University, Kate Rubin, is using this effect to study galaxies. So if you have a galaxy, galaxies are fun objects. There's gas in the universe. We talked about this a little bit. Some gas just out in space, and it gets gravitationally pulled into galaxies. So galaxies can build up mass over time and get bigger and bigger and bigger. But also, they have what I love, supernova. Supernova blow things apart. So gas goes out because of supernova. So you got gas coming in, gas going out, and there's this question of what's that balance? Are galaxies getting bigger? Are they getting smaller? How is this affecting? Are we getting recycled material? If you have a supernova, it makes these heavier and heavier elements. And do those just go off into space, or do they come back and seed the next generation of stars? So what she does is she does spectroscopy. She looks at a galaxy and looks at the outer regions of the galaxy by using background sources. So if you have bright sources in the background, the light travels through the galaxy, we get these absorption lines at those specific wavelengths telling us what it's made of. And then we can measure the velocities, or the line of sight velocities, and we can say this gas cloud is moving outwards, or this one's moving inwards. And so she can take a measurement of how much is going in and how much is coming out. How do you feel about that? It's a lot?
Wow.
Okay. So on that's what I had to say. So I hope I give you some idea of what research we do, and that we're scientists studying the universe, and we're trying to do it kind of with our hands tied behind our back because we can't measure things directly. We have to use just the light that we receive from the objects.
Thank you.
Thank you.